So before we get into our detailed discussion of the formation of ionic bonds, the first thing to cover in Lewis structures is typically something called the Lewis dot symbol. So the Lewis dot symbol is based on the element symbol, right, surrounded by its valence electrons. So the rule is this: as you put the electrons around the atom, it's kind of like Hund's rule. You don't pair electrons until you have to. Now, it may not make sense, but I'll show you how you can think about it. But just keep the electrons separate as long as possible, and basically there's a maximum of 2 electrons per site, so that's kind of like the Pauli exclusion principle. Now, this actually doesn't really have that much to do with like physical chemical reality, like quantum mechanics, but it is loosely related to how we do the structures and analyze them later. So it's not a totally bad thing to think of it like this. So for boron, right, I have 3 valence electrons. Now, how did I get the 3? Well, pretty simply, right, boron is in group 13, or which happens to be 3A. If you wanted this shortcut or simple way to do this is you just subtract 10 from all these, and that'll tell you how many valence electrons. On this side, it's just a number of the group. So hydrogen has 1, but so do everything else in this group. And beryllium has 2, as does everything in that group. So boron would have 3 valence electrons. And then when I go to draw the Lewis dot structure, I just go like this. Now, it doesn't matter which side you put it on, but we'll just use this to keep track of the valence electrons. For the carbon, we would have 4. Again, looking at it's in group 14 or 4A. We would just keep it like this. Now, nitrogen is the first one where you have to pair. So this is 5, and you would go 1, 2, 3, 4, and then maybe like that for 5. And then sulfur, even though it's a period below, would be 6 valence electrons, and radon would be 8. I left the halogens off, so this would be 1, 2, oops, 1, 2, 3, 4, 5, 6, like that. And then radon would be all 8, so we can go like this. So those are the Lewis dot structures, and we'll use this to represent valence electrons when we do ionic bonding. So we can imagine, right, how ionic bonds form between sodium and chlorine atoms. Now you have to remember this is actually Cl2, right? It comes from Cl2, and we'll talk about that in a bit when we do our little detailed description. But sodium atoms, right, are neon core and then 3s1, and they donate an electron to chlorine to form neon, right, basically neon plus 3s2 3p5, so you're going to add an electron to it, and this is what the electron configurations become. So chlorine, right, becomes like argon in terms of its electron configuration, and sodium becomes like neon. To finish this off, really to get the Lewis structure, we're going to do this. And I just wanted to point out, this is actually a redox reaction. So ionic compounds actually form through redox reactions from their elements. That is, the elements have to either gain or lose electrons. Now, a lot of times you learn in a Chem 3A class or a more introductory high school class that it's the noble gas electron configuration that drives this process. That is, gaining the electron for chlorine and losing the electron for sodium are good enough in terms of stability to form the sodium chloride ionic compound. And it turns out that's not true. Okay, so the main stabilizing force is not the electron configurations. So let's just think about like why that is. Let's say you have sodium, right? And you want to make sodium ion from it. Now, technically, when you do this, you do it in the gas phase, but let's just think about it conceptually like this. Let me get rid of the positive here. Now the plus sign, sorry. In order to do this, right, you have to separate a positive charge from a negative charge. And this is essentially ionization energy. So you have to add the ionization energy to this. Well, from what we looked at in the last chapter, but just conceptually thinking about it, that takes a lot of energy. So removing the electron from the sodium to give it to the chlorine actually doesn't make the sodium ion more stable than the sodium atom. It's actually less stable because you have to remove the electron. Now, it's a little less obvious for the chlorine what's going on because it does seem like the sodium gives the chlorine an electron, and so it should be happier this way. In fact, chlorine getting the electron is stabilizing. It's the electron affinity for chlorine, right? So I have a chlorine atom with its Lewis dot structure like this. I'm going to add an electron to it, which is going to make it Cl like this. And if you remember, chlorine, when it makes the chloride ion, this is what we call the electron affinity. And that's energy that gets released. And it could be conceivable that the energy released is more than the energy it takes to remove the electron from the sodium atom. But it's not, because in order to get chlorine, right, as atoms, it doesn't come as chlorine atoms. It actually comes as Cl2 gas. And then what you have to do is you have to break the Cl-Cl bond. It turns out that takes more energy than you get back from the electron affinity. So I've kind of summarized it like this, right? Sodium chloride is produced by this, which is the ionization energy. But it's also formed from this process. But this requires breaking a bond and the electron affinity. So there's a lot of details that we have to think about in order to think about where does or why does sodium chloride form when sodium metal is exposed to chlorine gas. Because by this reasoning, the sodium absorbing the energy and the bond breaking absorbing energy, the sodium chloride reaction should be actually fairly endothermic. But let's watch a short video. This comes from UC Berkeley, and they use it for their online general chemistry lectures.
We've asked Lonnie to demonstrate the formation of an ionic bond. In this case, the bond between sodium and chlorine in sodium chloride. So Lonnie's filled a beaker with elemental chlorine. That's chlorine gas, Cl2. It's a yellow gas. He'll also use solid sodium metal. Solid sodium metal is a shiny silver metal that's very soft. He can actually cut it with a knife. Sodium metal is very reactive. It will react in air and water, so it's stored under hexane. He'll pull off a small chunk and immediately store it under hexane while he prepares the rest of the experiment. Now, to get the reaction to go, he'll want to clean the sodium, make the surface very clean, and warm it slightly to help the reaction proceed. He'll do that by placing the sodium in a spatula and then warming it over a flame to clean the surface and to get the sodium warm enough to initiate the chemical reaction. Now, the reaction between sodium metal and chlorine gas proceeds, but we know the ionization energy of sodium is greater than the energy released, the electron affinity, when chlorine accepts electrons. So the reaction goes because the positive ions formed on sodium and the negative ions formed on chlorine are drawn together, a Coulombic interaction, to form an ionic bond. The formation of that ionic bond, plus and minus charges attracted together, releases energy, and that's the driving force for this chemical reaction. And you can see that it's exothermic. Energy's being released. Bright red glow, typical of emissions from sodium. Now the reaction between sodium and chlorine, of course, forms sodium chloride. We typically know that as table salt. And Lonnie's prepared some in advance. He has white table salt, purified, that he can show us. There it is, purified in advance from Lonnie Laboratories. And Lonnie tells me the salt that he makes in Lonnie Laboratories is far superior to any salt that you can buy in the store. So what does he have to do now? Lonnie's going to demonstrate, clearly hasn't had his breakfast this morning, that Lonnie Lab salt far superior to any salt you could buy in the store. Thank you, Lonnie, for that demonstration that sodium chloride, an important spice and food flavoring. And when you make it yourself, the satisfaction is so much more complete.
So I hope you noticed that there was a lot of energy released during that reaction. And we know that it didn't come from the formation of the sodium ion, and it doesn't form from the formation of the chloride ion, so what's left, right? And it really forms, as it said in the video, it forms from the sodium and chloride ions coming together to form the ionic bond. So this is kind of like a Coulomb's law thing again. I have oppositely charged objects are far apart, but they come together and they form this strong ionic bond, right? When they're close together, they'll be very low in energy, and all that energy has to be released, and that's the heat that you're seeing. And like you said, that's actually the emission spectra, or light that you see from emission spectra for a sodium lamp. So sodium chloride really forms because of what's called the lattice energy. It's the formation of the ionic bond from the ions in the gas phase. So the energy released when an ionic solid forms from its infinitely separated ions in the gas phase. In other words, what that means that an ionic solid forms from infinitely separated ions. That's just another phrase. Sodium ion, right, plus a chloride ion in the gas phase like this. This is known as the energy that's released from this process, the delta H for this is known as the lattice energy. Okay, and we'll just abbreviate that as LAT. Now, the guys who studied this initially and made it a popular way of studying these kinds of problems were Born and Haber. So we call this the Born-Haber cycle. And you'll see what I mean by a cycle when I lay it out for you. And it's pretty intimidating to look at it first. I'm not going to actually do a lot of examples of this because it's really well laid out in your book. I'll point you to this section for that. But basically uses Hess's law, how we can add chemical reaction heats to calculate the lattice energy of compounds. So let's sort of go over the process, okay? Now, when we're thinking about sodium ions and chloride ions coming together, that's actually what I wrote here. Right? But what I did was I added another component to this, and the vertical axis, this is energy. And high in energy would be less stable, low in energy is more stable. So the sodium and the chloride ions come together to release energy to form sodium chloride solid. Okay. Now, what Bourne and Haber did is they sort of envisioned a process where you could take sodium solid, right, and take it all the way up into the gas phase, and then chloride or Cl2 and form chlorine gas and then chloride, and then form the sodium chloride from the lattice energy reaction. And to make a cycle, and I'll show you what the cycle is in just a second. But in order to get sodium in the gas phase, we're going to start with sodium, elemental sodium. And when we take elemental sodium, we have to vaporize it. So the heat of vaporization, that is the energy it takes to go from the solid to the gas, can be looked up in the back of your book. Okay, it's in the appendix of your textbook. But if you look in the chapter, and I'll show you here in a second, they list all these values for you. Now, once you get sodium to the gas phase, you have to ionize it. That's this process that I was talking about here, that sodium has to be ionized. Now, ionization energies are measured in the gas phase. The easiest way to measure them is in the gas phase. So what you do is you take sodium solid to the gas and then you ionize it, and this is the ionization energy. So basically you have to add these energies up, right? And now you have sodium ion. For chlorine, the first thing you have to do is break the chemical bond that exists between the two chlorine atoms. And so you have to absorb that energy to form a chlorine atom. And then it'll accept the electron. Because remember, from here to here, all right, from here to here, it got rid of an electron. But from here to here, you're going to add an electron, and that's how you get the chloride ion. So this red arrow to the electron and this red arrow from the electron simply represent the same electron. The sodium's going to lose it, the chlorine's going to get it. Then you have the ions in the gas phase, which can come together to form the crystal lattice, is what I was talking about earlier. Now, you can calculate all the way up to here, and you can calculate all the way up to here, but you somehow have to close this loop, because it turns out we know everything going from sodium to sodium ion and chlorine to chloride ion, but we don't know the lattice energy. How far does this drop, right? And it turns out you can calculate this from the enthalpy of formation for sodium chloride, or basically Na solid plus 1/2 Cl2 gas makes sodium chloride solid. We can look those numbers and calculate them. So really, the other thing that comes from this is coming from sodium and 1/2 chlorine gas to form that product. And so we have all the numbers to calculate this one unknown number. Now I'm going to lay this out as equations, and I'll walk you through it and I'll show you the textbook. But the first step is to calculate the heat of reaction to form the sodium chloride, right? Then what you're going to do is you got to take sodium solid to sodium gas. So that's delta H of vaporization. Let me fix that. There's actually a couple things I had to fix on that. So this is just the heat of the reaction. This is sodium going to sodium the gas phase, so that's the heat of vaporization. And then it's the ionization energy. This is the energy required to form the sodium ion. This is the chlorine breaking the bond, so the dissociation to go to chlorine atoms. And this is the electron affinity. These are all values that you can look up in your book. And then the last step is that the process of sodium gas plus chloride gas, right, makes sodium chloride. This is what's going to give us the lattice energy. And I did notice one more fix. I had put a hyphen in there, got rid of it. So it should just look like this. Now let me show you what it looks like in your text. Now in your textbook they go through, and this is the Born-Haber cycle, right? And again, a little pointer to Hess's law. But this is the heat. This is the heat of the reaction, right? from standard enthalpies of formation. And then we have going into the gas phase. They list that value for you, but you can get it from the back of your book. Then they talk about the bond breaking energy, right? And then they talk about the ionization energy. Notice these are all endothermic. The only exothermic process is this one here. That's the electron affinity. And then they want to know what this energy is. What is the lattice energy? So let's take a look at these in a little different way. And this is where we start using Hess's law. So I'm going to draw a line on here to separate this from the rest of it, because I'm not going to include this in what I do. So I'm going to add these two reactions together. And when I do that, what happens? Well, the sodium gases actually get to cancel out. So I can do this. Now, let's take a look at the reactions for chlorine. For the reactions for chlorine, I can actually look at, let's say I add these two reactions together, right? Then what I get to do is I get to cancel out this. The other thing I get to cancel out now, though, think about what's going on. I'm going to combine all of these together. And when I combine all of them together, what happens? Well, the sodiums, I've already canceled out these guys and these guys. But I can cancel out the electron here. So it's like balancing a redox reaction. So I'm going to get rid of that electron. So if I add all of these things together, right, and I get a reaction, what do I get to do with Hess's law? Well, I just add all of these things together, right? But now look what happens when I add this reaction to these reactions up here. The sodium gets to cancel with the sodium up here. And the chloride gets to cancel with this guy here. So what am I left with, right? I'm left with sodium plus 1/2 Cl2 makes sodium chloride gas. And what is that reaction? That's actually this reaction up here. So what Hess's law says is the heat of reaction here is the same as the sum of all of these together, because when I add all these reactions together, right, I get sodium, that's sodium, half a chlorine, that's half a chlorine, makes sodium chloride solid, right? Well, that's supposed to be sodium chloride solid down there. There's another mistake. Yeah, so it makes sodium chloride solid. Sorry about that. Like 3 mistakes on this one slide. So what that means is I can write the following, that delta H of the reaction is equal to delta H of the vaporization plus the delta H of the ionization energy plus the delta H of the dissociation plus the delta H of the electron affinity, right? Plus the delta H of the lattice energy. And now what I can do is I can just solve this for this. So I'm going to take the heat of the reaction, I'm just going to subtract all of these values off of it, and I'll have found the lattice energy. Now, rather than do that, since the book already did this particular example, I'll go ahead and show that to you out of the textbook. All right? So they said, in essence, the same thing that we did here. They just called them step 1, 2, 3, 4, and 5. You plug all of those values in, right, and you solve for the lattice energy. So they rearranged it. It's minus 788 kilojoules per mole, and that's quite a bit of energy. That's why when the reaction takes place, it happens very quickly because the atoms or the ions are in the gas phase. And then the other thing that happens is that a lot of energy gets released as those ions come together, and that actually helps to speed up the reaction. They also showed the Born-Haber cycle like this. Okay, I just preferred to show it the way that I did, so I could talk you through it a little bit easier. That diagram is actually very difficult to talk through. So it's a cycle, right? Coming back to the sodium, starting from the sodium here and going up through the cycle and back to the sodium chloride. And then starting from the chlorine, going back up through the cycle again to form the sodium chloride. Then you can, that's a closed loop. It allows you to calculate this one unknown value. Let's talk a little bit about the general properties of the lattice energy. So let's think about a couple of different things. Let's say I have a positive ion and a negative ion, like this. Now, what determines how much energy is released when these two ions come together, right? Now we have to think in terms of Coulomb's law. We say that the E, the potential energy that's of that association, is going to be a constant, and then it's Q1, Q2 over R. So there's a couple of things that can affect the magnitude of the energy. One is just the value for the radius. This would be R, or the ionic bond length. Okay, so imagine that you're looking at sodium and chlorine to form sodium chloride, or potassium and chlorine to have potassium chloride. I want to put plus here and minus, although we don't normally write it when we write the ionic compounds. How are these two different, right? Which would have a greater lattice energy? Now, it looks like, well, they're both plus one, minus one, right? So what's the difference? The difference is where potassium and sodium are on the periodic table. So if you're looking at potassium and you're looking at sodium, right? Sodium is further up on the periodic table. Remember, the trend for radius, it starts at the bottom and moves up. And this is true for and gets smaller as you move up. And this is true whether or not it's sodium and potassium, the metal, or sodium or potassium, the ion. As you move up, they get smaller, right? So what that means is when you look at the lattice, the radius for sodium chloride, the ionic bond radius, has a smaller bond radius. What does that mean, right? It means it has a larger lattice energy. So smaller ions will produce a general property of the lattice energy is smaller ions of the same charge produce greater amounts of energy that's released or have a larger lattice energy. So smaller ions, write this down here. And so in order to do that, right, you really have to know what the periodic trends are for both the cations and the anions and be able to compare cation and anion sizes as two things come together. Typically the variations, though, only include variations in one of the ions and not both of the ions. So ionic radius is an important feature in determining relative lattice energy. So that takes care of R. What else matters, right? Well, let's say you're looking at Mg2 plus and Cl, right? That's going to be MgCl2. You actually have a couple things going on here. Compared to like sodium chloride, we would expect this to have more lattice energy for a couple of reasons. But one is primarily you have a +2 charge here, right? And you're forming two ionic bonds. But in just terms of ion charges, if you double the charge, you double the lattice energy. And so when you look at the lattice energies of divalent, that is +2 charge ions, or trivalent, +3 like aluminum ion, they have very large lattice energies simply because the charge is so much bigger, and you're also forming more ionic bonds as the compound is being formed. So the other aspect of properties of lattice energy is that ion charges, I have a hard time writing on my screen right now, ion charges high or larger ion charge means larger lattice energy. I'm running out of space here. So those are two primary things to think about when you're thinking about lattice energy, and most of it comes from Coulomb's law. That is, radius matters because the closer they are, more energy can be released. Or charge matters because if it has a larger positive or negative charge, you end up having more energy released because it's directly related to the potential energy of attraction or force that's holding the two ions together.